So I'm Fionn. I'm working at Livermore 2, and I'm going to talk to you about how you can actually run an AFQMC simulation in QMCpack, mostly through PySCF. So the simulations are the workflow is much simpler than a BMC workflow in the sense that you only need the one and two body matrix elements, some sort of factorized form of the two electron integrals and a trial wave function, which is a n by n matrix of molecular orbital coefficients. So in principle, these can come from any code that you like. Any molecular, any quantum chemistry code can in principle generate these, I think, or at least you can generate them from the output of quantum chemistry code. So in principle, you can use any quantum chemistry code you like. For solids, we're mostly reliant on PySCF right now, but that will change in the future. The tools you need to generate the QMCpack input can be found in utils under the main QMCpack repository in AFQMC tools. And the main script that you might want to use if you're running PySCF calculations is called PySCF AFQMC. So I'll just go through how you run this now through the simple workflow for a molecule. And this is the first example in the set of tutorials, which has a more detailed README about how the whole process works. But this is, if you're familiar with PySCF, a standard PySCF calculation. We're just specifying where to store the output of the SCF calculation. So there's nothing new here. Step 2 is you just run this converter script. So there are various options, which I'll go through in a second. But in the simplest case, you have an input, which is the SCF input from PySCF. You have an output name where you're going to store the Hamiltonian, and in future iterations, the wave function. There's a threshold parameter here, minus t, which specifies the convergence threshold on the Cholesky decomposition, which is a convergible parameter, which you'll have to check yourself. And the final option will generate a AFQMCpack input file based off of this Hamiltonian, so you don't have to do anything further. And then finally, you can just run the code wherever you like. And I should say for the tutorials, you should use the complex build of QMCpack, just because all of the integral files have been generated assuming complex two-electron integrals.
It's actually available called QMCpack_complex. I think that's
okay. I should just say, when you're compiling QMCpack yourself, you have to explicitly tell it to build the AFQMC source code. So you can find that in the documentation. So molecular calculations through PySCF are relatively straightforward. It's just it requires zero modification to your regular PySCF workflow. For solids, which there are 2 examples of in the repository. There's an additional step here after you run your SCF calculation. Here I'm doing restricted Hartree-Fock with k-points. So in your PySCF input, you have to store the Fock matrix and this rotation matrix to an orthogonalized AO basis. This might change in the future, but just know that this is an additional step that you have to take care of in your SCF calculations in PySCF. This is mostly done because for large systems, this Fock matrix can be relatively expensive to compute, and we didn't want to do it in the integral generation step, but that might change in the future. And the integral generation step proceeds as before, so PySCF to AFQMC. If you're running a supercell here, so without k-point symmetry, then the integral generation step proceeds exactly as it would for a molecular calculation. If you want to use the new algorithm using k-point symmetry, you can just pass minus k to the integral generation script, and it'll generate the Hamiltonian with that k-point symmetric form. So if you want to learn more about the various options available to you, just pass help to the script. The only other options available are GDF, which means use Gaussian density fitting, which isn't currently in the development version of the repository, but will be coming soon. And for molecular calculations, you can specify a cast in the form of a comma-separated list of n and n for number of active electrons and orbital. And then it will generate the Hamiltonian in this cascade. So there are a number of, 7 tutorials available in the workshop repository. I would start at the first one because they're less descriptive as you go down the list. So the first one has a very detailed README about how to workflow, AFQMC workflow, how to generate the input, and some explanation on the various input options. Then I just go through the various options you can use with the integral generation script, namely doing a frozen core calculation, generating a UHF trial wave function, generating different forms of trial wave function, say if you want to get them from your own code, how would you go about doing that? This step is important if you want to use backpropagation because there is an additional convertible parameter, namely the backpropagation time, if you want to compute backpropagated RDMs, for example. So this example goes through how you would check the convergence of backpropagated quantities. And then finally, there are 2 solid-state examples. Diamond 2x2x2 in the regular supercell form, which just assumes no symmetry and reads the integrals as just a sparse Cholesky 3-index quantity. And finally, an example using the k-point symmetric integrals. You have to run 6 before you can run 7. This is a note. Okay, so that's using the script, which is exclusively for PySCF. If you have a more complicated workflow, you can use PySCF tools as a library. So if you want to, the 4th example goes through this in a bit more detail. I just cooked up some example here, like Anwar was saying earlier on, if you wanted to check different trial wave functions, and say you had run RHF, UHF, and TBE SCF calculations. Now what you could do is you could generate a single Hamiltonian in a common basis set. We use an orthogonalized AO basis set. So this function just generates a Hamiltonian from a molecular PySCF object, read from this loading step here, and then you could just loop through the checkpoint files and generate a wave function for each one of these SCF from each one of these SCF solutions. So there's this write wave function null, which writes a wave function for a molecular PySCF object. In future, all of this thing will be done through HDF5, but at the moment it will be written to a plain text ASCII file specified by this name. So if you want to, if you don't want to use PySCF, but you have some other means to generate your Hamiltonian matrix elements, then you can just, we have this helper routine, which ultimately is used lower down the call line, called write QMC pack Cholesky, which just takes the core Hamiltonian, either NumPy arrays, and the Cholesky factorization, or some 3-index quantity in sparse format. So here, I just generated some random permission matrix. I computed the electron repulsion integrals random again, positive semi-definite matrix. Then I called the Cholesky factorization of this from NumPy, and I just generate a sparse matrix CSR format from this Cholesky factorization. And once you pass that through, it will generate a Hamiltonian called hamil.h5, which will be in a format readable by QMC pack, AFQMC QMC pack. So if you have, for instance, some quantum chemistry code which generates this information in plain text or some other format, then it should be fairly easy to get these quantities out through Python. And I can help you with that if you have any questions. Also, for wave functions, which is maybe the more where you might have better ideas how to generate better wave functions. Again, there's this helper function, which Miguel was saying earlier. There are 2 formats for QMC pack wave functions. There's non-orthogonal multi-slater determinants, and there's also particle hole multi-slater determinants. So there's 2 routines, which will cause write non-orthogonal MSD wave function, or write particle hole MSD wave function, which will take a wave function in some format. So for a non-orthogonal multi-slater determinant, we expect some matrix of shape, the number of determinants, the number of molecular orbitals, and the number of electrons in your system. And once you can write your wave function in that format, you can pass it to this routine, which will then generate a wave function readable by QMC pack. So you can use any quantum chemistry code you like to generate your trial wave function. Very simply. And if you really, really want to use OCI dumps, you can. There's another script called FCI dump to AFQMC, which will take A-fold symmetric real integrals in OCI dump format and generate the AFQMC input from that. I really wouldn't advise generating FCI dumps. It doesn't scale. It's a waste of time. Okay, that's more or less it. I think it's fairly easy to run AFQMC through Python or through these Python tools. PyCF is the easiest way to do so at the moment, but it should be fairly straightforward to adapt whatever your favorite quantum chemistry code or solid state code is to use these tools. These tools are only pushed to develop like 2 weeks ago, so some of these most of these features are stable, but some features will be deprecated. Most notably, the ASCII wave functions are going to be gone soon, so I wouldn't look into them in too much detail. Yeah, so that's what I said here. If you have any issues, open them on GitHub, and I acknowledge funding support. Thank you.
Thanks, Fionn. So questions for Fionn or indeed Miguel on auxiliary fields? Maybe it's right up.
So Miguel mentioned 100 of atoms as a target, 200 of atoms.
Yes.
How many electrons are you thinking about? Because it can be plutonium.
Hundreds of electrons, 500 electrons.
500 electrons.
Is that roughly right? 200, 500 electrons. It's like maybe 3,000 bands, 500 electrons. Yeah, that's really good.
So related to that, it might be possible to do a defect calculation in the future, or I think that might be pushing it too much. So that's a few hundred atoms and low symmetry.
It should be possible. It's always
Usefully converged.
Yeah, I don't know. Basis that could be an issue with this, unless there's some cancellation of errors.
Questions? Okay, so perhaps it is more straightforward than real space.
A question with the previous talk. I don't know, Miguel is still here.
I'm here, yeah.
When you mentioned that you calculate the energy using a tri-wave function that was different than the one you used to drive the bias.
Right.
It's an observable, right? So
yeah. How can you transfer that energy? Just a projection.
No, so it is an estimate. So when you do the projection, you generate the sample of walkers, and you measure an average with respect to that. So you are doing resampling. It's not as trivial as I make it sound, right? So now the average is you have to average numerator and denominator independently, and then do the ratio of the average. But it's perfectly correct mathematically. You are doing reweighting essentially. So you have a certain weight given by the propagating wave function. You have to multiply and divide by the ratio of the old to the new weight times the local energy of the new wave function. And then you have to independently estimate the ratio of overlaps. And when you average those, the ratio of those two. I've done this for the Chromium diagram, which is really hard. And that allows me to do 1 million determinants for propagation and maybe 50,000 determinants for energy, or 1 million particle Hall determinants for propagation and an orthogonal wave function for the energy, and it just mostly converges to the right value.
Yeah, the projected energy estimator doesn't rely on the left-hand wave function being related. If you have an exact current state wave function, then the projected energy estimator will always give you the exact current state energy, so regardless of the trial wave function on the left-hand side.
If you look at all the papers, they're always assumed the same, but nowhere is there a direct connection between the two. So we haven't written it up, again, as many things, but eventually we will get to some deadline where we have to write it up, and it's perfectly mathematically.
Okay, it gives you a number that is very similar.
Well, it depends on what you're putting in, right? So if you have a full wave function and you put a much more expensive one, it will be better. The error formally is we say quadratic, but there is a piece that's actually linear on both sides. If you do the expansion in terms of the different terms, typically the quadratic term in terms of the trial wave function comes. There's also a term that is linear on both sides. And so if you make the trial wave function sufficiently bad, that will give you a worse energy, regardless of what the wave function that you're projecting is.
All right. Thanks very much, Fionn. And Miguel, much appreciated.